Hello? Hello?
Good afternoon, madam.
Good afternoon. Yeah. Is it okay now? Clear?
Yes, madam. Okay, madam. Clear.
Yeah. Is my screen visible? Hello?
Yes, madam. It is visible, madam.
Okay. Good afternoon, everyone. Yesterday we had encountered a problem. We had to stop in between. So we started the calculation of chemical shifts of various carbons in the organic molecules. And today we are going to discuss them at length. Okay. Calculation of chemical shifts. We can calculate the chemical shifts of alkane carbons. In fact, all types of carbons. Let us first start with alkanes. Alkanes carbons chemical shifts can be calculated by using a simple equation that delta is equal to minus 2.5 plus summation of Na. Here minus 2.5 is the shift for methane. A is the additive shift parameter.
Epsilon kada madam. Minus 2.5 plus epsilon Na.
Yeah, summation, that is summation.
Summation అంటే అడిషన్ కాదు మేడం. ఎప్సిలాన్ అనేది ఒక కాన్స్టెంట్ కదా మేడం.
ఎప్సిలాన్ కాదు, యాక్చువల్లీ అక్కడ ఎప్సిలాన్ వచ్చింది. We need to sum it.
Okay, ma'am.
Summation symbol it should be there.
Okay,
that by mistake or print mistake. It is a summation of all these shift values only. Minus 2.5 is the shift for methane, and we have to add all these additive shifts to this minus 2.5 to get the calculated chemical shift of carbons, various carbons in alkanes. Okay. Here, this is a table. You need to remember this. Here, carbon 13 atom. The carbon 13 atom that is contributing to the additive shift of this chemical shift. Shift for the carbons under consideration. Suppose alpha is additive shift is this much 9.5, beta 9.4, gamma upfield shift minus 2.5, and delta 0.3, epsilon 0.1. And all this primary carbon, if it is a primary carbon attached to tertiary carbon, minus 1.1. Primary carbon attached to quaternary carbon, it is minus 3.4. And second, if it is a secondary carbon attached to tertiary carbon, it is minus 2.5. And if it is a secondary carbon attached to quaternary carbon, it is minus 7.2. And if it is a tertiary carbon attached to secondary carbon, minus 3.7. Tertiary carbon to tertiary carbon, it is minus 9.5. If it is a quaternary carbon attached to primary carbon, it is minus 1.5. And quaternary carbon to secondary carbon, it is minus 8.4. So these values you need to remember to calculate, because they are few only, so you can remember, because in the examination they may ask to calculate the chemical shift of a simple alkanes. So you need to remember this table. And I'm going to explain this with a simple example by calculating the chemical shifts of 3-methyl pentane. You see here how many non-equivalent carbons are there? 1, 2, 3, 4. Actually 1, 2, 3. And this one, 4 non-equivalent carbons are there. 2 and 4 are same. 1 and 5 are same. So you get 4 signals in the C13 NMR spectrum. So how we can calculate? See, this 3-methyl pentane, if you see, this is 3-methyl pentane, and we are calculating the chemical shift of one carbon, this one. So this one carbon has got how many alpha carbons? Hello?
Ma'am.
No problem. Yeah. Here, how many alpha carbons it has got? 1 alpha carbon it has, 1 beta carbon, and 2 gamma carbons. This and this 2 gamma carbons with respect to 1 and 1 delta carbon. So all these values, shift values, we need to incorporate here. See, C1 carbon has 1 alpha carbon, 1 beta carbon, 2 gamma carbons, and 1 delta carbon. So we have to incorporate these values into the formula that is given. Delta C1 is equal to minus 2.5 plus 1 into 9.1 alpha carbon additive shift and 1 into 9.4 beta carbon additive shift, and this is gamma carbon additive shift 2 into minus 2.5, and this is delta value. Okay, if you just add it up, 11.3 it will come. So this is the calculated value. See the observed value, it's so close, 11.5. 11.3 is the calculated value and observed value is 11.5. So most of the time they're almost nearer to the chemical shift value of calculated one. Okay, then delta C2. If you see delta C2, this carbon has got how many alpha carbons? 1 and 3.
1.
2 are, no, 2 are there. This one and this one.
No, third one and first one. Okay, ma'am.
And then how many beta carbons? This and this, 2
Yes,
beta and 1 gamma carbon.
Yes, ma'am.
So you just substitute those values. C2 carbon has 2 alpha carbons, 2 beta carbons, and 1 gamma carbon, and it is the secondary carbon. It is the secondary carbon attached to 1 tertiary carbon. Okay, which tertiary? This is the tertiary carbon. Secondary carbon attached to 1 tertiary carbon. So that shift also we need to add. See, simply I am adding. You just check the table and substitute those values, and you will get add it up. Then you get 29.5 ppm. So delta C2 calculated is actually 29.5 ppm. You must write these values. And observed value is 29.5 ppm. It's exactly same. Okay, so this is how you can calculate the chemical shifts of various carbons. And let us see the third one.
మేము ఇప్పుడు ఒక ఎగ్జాంపుల్ దగ్గరికి వెళ్ళండి మేడం ఒకసారి. సో ఇప్పుడు సెకండరీ కార్బన్ టెర్షరీ కార్బన్ అటాచ్ అయింది. టెర్షరీ కార్బన్ మళ్ళీ అక్కడ వేరే దానికి కూడా అటాచ్ అయ్యింది కదా మేడం.
That shift is not there in this. You check the table. The shift, if it is there, you can add that. If it is not there, that is not contributing to the shift.
Okay, ma'am.
Okay.
Okay, ma'am.
Now, see, that is the value is delta C2. We have calculated, and it is 29.5, and observed also 29.5. Very just exact. Then you can calculate the chemical shift of delta C3. If you see the 3 carbons, 3 alpha carbons are there. 2, 4, and 6. 3 alpha carbons, 2 beta carbons, and no gamma carbon here, isn't it? And it is the tertiary carbon attached to secondary carbons and primary carbon. I don't think shift parameter is there in here. So let us see. Okay. So delta C3 3-methyl pentane has 3 alpha carbons, 2 beta carbons, and it is a tertiary carbon attached to 2 secondary carbons. This one and this one. Okay. And you add those values again. Then therefore it will be minus 2.5 plus 3 into 9.1, and this comes to 36.2. You can calculate it at home later. Okay. Then calculated is 36.2. Observed, you see 36.9. Very close, is it not? So that way you can calculate. And next, last one is 4th carbon. This one. So how many alpha carbons? 1 alpha carbon, 2 beta carbons, and 2 gamma carbons. Let us see how it is coming. It has got 1 alpha carbon, 2 beta carbons, 2 gamma carbons, and it is a primary carbon attached to 1 tertiary carbon. See, it is a primary carbon attached to 1 tertiary carbon, for which additive shift is there. Primary carbon attached to, see, tertiary carbon minus 1.1. You have to add this, and you will get 19.3. And observed value is 18.8. So it's quite close. Okay. So that way you can calculate for any given alkane, simple alkane. And once you calculate the alkane chemical shifts, and later on you will have additive shifts based on the substitution, which I am going to discuss later. And that if you simply incorporate it into the these values, then you will be able to know calculated approximate values of the even unknown molecules. And in fact, so many tables are there, C13, and there you will get calculated chemical shifts also. In fact, you can get in these values in ChemDraw also. So which will be which will be compared with the observed one. That means they are just guiding, they just guide us in the analysis. But in the end, we have to take the spectrum and spectrum of the unknown sample, or if it is a known sample, then compare with the known value, that calculated values, so that we can confirm the structure actually. So this is the advantage of C13 NMR. So you can calculate it also, and you can get prior idea where exactly you can expect the chemical shift output of the carbons for the molecule under consideration. Okay, next. Some more examples I am giving you, just, and you can calculate, you can just for the practice purpose, you can calculate later. See, N-hexane, it gives 3 signals because 1, 2, 3, so 1 and 6 are same, 2 and 5 are same, 3 and 4 are same. So it gives 3 signals and values I am giving you. You can, by incorporating these values into the equation given, you can check how much calculated values you are getting and compare with these observed values. Okay, and this is another example, 2-methyl pentane. So here also how many, all are different here, 1, 2, 3, 4, 5, 1 and 6 are same, and therefore it gives 5 signals, C1 and C6 this much, and these are the values, observed values, not calculated. These are the values given. You can compare by calculating the chemical shifts. Okay, now see, we understood now we can calculate the chemical shifts of various parent alkanes by using that equation. And now suppose, because we will be having various substitutions. So what happens if there are substituents attached to the alkanes? That's how we get different organic molecules, right? Alkanoic acid means COOH is substituent, ester, amide, etc. Okay. So suppose COOH is attached. If it is an alpha carbon, the carbon under consideration which we are calculating is terminal 1, it contributes to 21 ppm shift. If it is internal, 16 ppm shift. Alpha terminal this much, beta terminal this much. You just observe the table. So all these substitutions, if they are attached to the alkane carbon, they will contribute to these shifts. You need not memorize this table, don't worry. This is such a big table. Just you can compare by calculating calculating some of the chemical shift values of the known compounds. For example, butanoic acid. You try to calculate the butane chemical shift first, then attach COOH to that, and then add these values, and then you will get the calculated chemical shifts. Okay, then these are the chemical shift values, ranges I'm showing you. This already I have given you. Just these alkane carbons fall in this range, and secondary carbon little bit downfield. Tertiary methane carbon some more downfield, quaternary even slightly more downfield, and if it is attached to halogens or hydroxy, etc., up to here, acetylene carbons in this range, and alkenic carbons in this range, in this place, and these places, where you get the signals for such carbons. If it is aromatic carbon, also almost nearer to alkene, little beyond alkenes, and nitrile slightly upfield than alkenes, and then amides, esters, carboxylic acids like this here, and in the end you will get carbonyl, that is aldehyde and ketocarbonyl. So this is the broad range. This range you must remember, just a range, approximate range. So that if you check the C13 NMR of any molecule, you will be able to know what type of carbons are present in the molecule and what is the hybridization state, whether aromatic ring is there, etc. Okay. So these are the values, approximate values of chemical shifts. This already I have given you, so I'm not going to discuss it here. Tetramethyl TMS is taken as 0, and these values already I've given before in the table, just similar to that. These are the values. See, ketone 190 to 220, and ester and acids 165 to 185. Everything is given in previously. Okay, so you just try to remember those ranges. Now, I told you, once you have the chemical shift of parent alkane, you can calculate the chemical shift of substituted alkanes also. How? See, this is the parent alkane pentane for 3-pentanol. 3-hydroxypentane or 3-pentanol. This is the, suppose without OH, it is pentane only, no? So if it is pentane, you can calculate with the formula given just now we have seen. Suppose if you calculate, these are the values you get. Now, OH is attached. So for that OH, that shift you have to add. Suppose if you are C alpha and 3-hydroxypentane, delta C3, this one. In 3-hydroxypentane, actually, this value to 34.7, we have to add what value? We have to add the this one. It is internal, no? So this value we have to add 8. See, 8. This 34.7, you have to add 4.1. Okay. This one. C2, beta in 3-hydroxypentane. C2 is beta to this one, 3-hydroxypentane, beta carbon. So beta carbon chemical additive shift is how much? It is 8. Beta carbon, beta internal. Okay, beta internal OH. Okay. This one, 8. So that is what is added. And then next, C3 in 3-hydroxypentane. This C3 in C3-hydroxypentane is what? Here we have to, which one we have to take? This one. (3-hydroxypentane), C3 in 3-hydroxypentane. 3 value we have to take. Actually, there is some jumbling, I think, here. So to this value, we have to add hydroxy substitution increment. Okay, this 8. So gamma, anyway, it is not there, so we will not be adding to that. And similarly, suppose 3-hydroxy pentane we have seen. Similarly, you can suppose you have 3-fluoropentane. Then these values you have to substitute, take down the positions, and accordingly you suppose if it is say 68, when we should add, for example, methane, you have, let us say methane chemical shift is -2.5, right? And methyl fluoride, so what, minus 2.5 to -2.5, what you have to add? This 68 you have to add. Then you will get approximate chemical shift of methyl fluoride carbon. Similarly, if it is ethyl fluoride, that second carbon, in ethane, you can calculate ethane chemical shift from the formula given. So to that, what we have to add? This 68 we have to add. Okay. And to the beta position 9.
Where is an example? This concept, madam.
ఎట్లా ఎగ్జాంపుల్ మీన్స్
ఇప్పుడు ఈ మాలిక్యూల్ సరిగ్గా ఇలా వాల్యూస్ అక్కడికి మ్యాచ్ కావట్లే కదా మేడం.
No.
Actually, in first one it is 41 only, ma'am, not 4.1.
But if it is 41, then why it will be 75.8?
See alpha.
Okay. Yes, it should be 41, madam. Yes, it should be 41. No, it is there in the table, madam. Then it is there in the table. 41 value is there in the table.
41 is there in the table.
Yes, it is there.
If you add, it will not be 75.8. Nice,
Yes,
right?
ma'am.
41 if you add, it is there. Alpha. Yeah.
Yes, madam. Here it is there, internal.
That's what I was referring to.
Yes.
If it is terminal, say, if it is not 3-hydroxy, suppose hydroxy is here, let us say, OH, then it is terminal, no? So to this, you have to add, not 41, 48 you have to add.
Okay.
Understood? If it is
Yes,
internal, this value. If it is terminal, this value. Suppose if it is OH, 41, because it is internal, no? 3-pentanol is internal alcohol. Terminal means it will be OH.
External. Okay, ma'am.
Terminal carbon. So same way, same, just if it is fluoride, let's say, simply we will substitute with fluorine, or instead of OH, let us substitute with fluorine. Then what will be the value? What will be the value? So see.
It will be 68.
63 plus that value.
Yes, madam. 63. It will be 63.
Right.
Internal.
Element is 63.
Yes,
and to this value we have to add. To this
yes,
value. So understood now?
Yes, ma'am.
Yeah.
Yes, ma'am.
Similarly, you can substitute with any group, NH2. Let us say 3-aminopentane.
Yes,
3-aminopentane, how much we have to add? 3-aminopentane, you have to add how much? How much is there? 3-aminopentane internal, no? So
yes, 24.
24 we have to add. If it is terminal, we have to add 29.
29.
Okay, understood?
Yes, ma'am.
I know, same thing. These values, just approximate value. These values you need not remember actually. Once you, you practice the analysis of spectra, you yourself will be like knowing approximately how much shift you can expect from the attached substituents. Once you are, thorough with it, experienced in that, once you practice more problems, so then you will know without this like table. This table is only just to help you to understand. Okay.
Okay, ma'am. Okay, ma'am.
That is why I took simplest example, methane. Methanol means to methane value minus 2.5, you have to add 48. Minus 2.5 plus 48. That will be the chemical shift of methanol carbon, like that. Okay. Methyl fluoride, you have to simply add 68. Methyl amine, you have to add 29. Okay. And toluene. Same thing, okay? Just you have to add. See, some more representative cycloalkanes chemical shifts are given here. Cyclopropane, all carbons are same, minus 2.9. Sigma electrons shielding, and this cyclobutane, all these values, approximate values, and this also you need not remember, just for reference. Now, we have seen the calculation of chemical shifts of alkanes and also the calculation of chemical shifts of substituted alkanes. And how you can calculate the chemical shifts of alkanes. See, alkanes, you have, if you have one double bond, you have 2 carbons. Need to calculate the chemical shifts of 2 carbons. Suppose this is the schematic diagram of an alkane. Here, let us if we are considering the calculation of this carbon, let us say this carbon has got 1 alpha carbon, 1 beta carbon, 1 gamma carbon. So to this carbon, this will become alpha prime, this will become beta prime, this will become gamma prime. And for this carbon, if you are calculating the chemical shift of this carbon, then this will be alpha, beta, gamma, and this other side one will be alpha prime, beta prime, gamma prime. You can write down here for this carbon, these are alpha, beta, gamma. Down you can write. And for this carbon, these are alpha, beta, gamma, and these are alpha, beta, gamma, and the other side alpha prime, beta prime, gamma prime, like that. Okay. So these are the chemical shift values, additive shift values. Alpha 10.6, beta 7.2, gamma minus 1.5. This gamma always, you see, always it is upfield shift. It is due to the steric compression, gamma Gaussian interaction, we call it. So always gamma carbon or gamma substituent induce upfield shift. That is why minus increment, minus value is there. So it will be always upfield. Normally gamma carbon will be upfield if any substituent is there. So similarly, alpha prime contributes this much, beta delta prime contributes this much, gamma prime contributes this much, and if it is a Z alkene, minus 1.5 Z correction. So I am just taking one example here. So just calculation of alkene carbons chemical shifts in 3-methyl-2-pentene. 3-methyl-2-pentene. Here we are calculating the chemical shift of these two carbons, C2 carbon and C3 carbon. C2 carbon, first let us see, C2 carbon in 3-methyl-2-pentene has how many alpha carbons? 1 alpha carbon, 2 alpha carbons, only 1 alpha carbon, 2 alpha prime carbons, you see. This and this. And 1 beta prime carbon, 1 beta prime carbon. So you just substitute these values. C2. This is the parent alkene. Parent alkene is ethylene. Ethylene value. This in case of alkenes, what we have said, we have added methane value, right? Here, this is parent alkene is ethylene. So ethylene chemical shift value is this. Sometimes in the examination they will ask this also. Ethylene chemical shift value, benzene chemical shift value, methane chemical shift value. Only that you remember. Okay. So C2 123.3. To this we have to add these increments, and it is a Z alkene. You see, well, two groups are on one side. This is Z alkene. So Z correction also we add minus 1.1. So 1 alpha carbon 10.6, 2 alpha prime carbons 2 into minus 7.9 plus 1 beta prime carbon 1 into minus 1.8 plus minus 1.1. So if you calculate 115.2, it will come. So observed is not given. That's why that question mark is there. So observed, we have to find out, check the values. Okay. Now it will be nearer only. It will be nearer, though it is not. I didn't get it from the books. We need to check more literature. It will be nearer only 115.2. It will be somewhere between 116 and 117, such that. Okay, but since I don't know exactly the value, I have not given. It is not given in the book also. Okay, that's why it's question mark is given. Delta C3. Because observed value, you have to observe the spectrum, or you have to get the from the literature. Calculation, you can do it, but observed value, you need to have some authentic source. So from the book or by observing the spectrum, we can get it. But it will be definitely between around 116, 117 only, because we see many spectrum. So in that, it will be observed like that only. So delta C3. C3 carbon has 2 alpha carbons. See these 2 alpha carbons, 1 beta carbon, and 1 alpha prime carbon. And these are the values. And Z correction also you need to add to this also. So observed is calculated is 142.7 and observed is 137.2. So plus or minus 5 to 6 ppm will be there. And this is almost nearer. Okay. So that's how you can calculate the chemical shift of any alkene carbons by simply substituting these values. And these values are only few. This also you need to remember for the examination sake. Okay. Next. See, representative alkenes, I am giving you some. You can calculate these values also. You can check yourself. See, propene, these are the values, and 2-butene, these are the values. Because this 17.6 is to which carbon? This carbon, because the alkane carbon, and these two are same, that is 126. And here you see 2 internal alkane always downfield than terminal. This also you must remember, always terminal alkene carbons are upfield than internal alkene carbons. So internal alkene is downfield 140, and this will be even further affected by various other substituents, which we will be discussing in the factors affecting chemical shift. So these are just some representative examples I have given you just for reference. You need not memorize all these values, just observe where alkene carbons are coming. See, around 123. Isn't it? And C 126. That means it's nearer to 123 alkene with ethylene chemical shift. And here also C 124. So here terminal and internal different. Now chemical shifts of alkynes. See, normal range of carbon is 65 to 90 ppm. We've already discussed this. And sp3 carbon attached to alkyne is shifted upfield by about 5 to 15 ppm due to anisotropic effect. Do you remember that proton in number, the acetylenic carbon, and that acetylenic proton is shifted upfield due to anisotropic effect of alkyne pi electrons, isn't it? Similarly, here also it is not hydrogen, the carbon that is in place of this one, this hydrogen. Actually in proton NMR, this will be shifted upfield. So here carbon also is there. This also will be shifted upfield as compared to ethylene. Acetylene will be upfield because acetylene due to anisotropic effect. Otherwise, actually acetylene is more electronegative. It should come downfield, but it is not just electronegativity. Anisotropy also contributes to the chemical shift. I'll discuss in the factors affecting chemical shift there. So always you see a carbon attached to this one, this carbon. I'm talking about acetylenic group, and this carbon will be shifted upfield, these two. Okay. See, here you see C2 and C3 only values are given, and these alkane values, it will be shifted upfield normal from the normal alkane, that means ethane value. Okay. And now benzene. Basic benzene value is 128, and similarly substitution of calculation actually should be calculation of monosubstituted benzenes, values of monosubstituted benzenes, it should be. This is also going to mistake. Substituent effects of in monosubstituted benzenes. See like this. If it is fluorine, direct ipsocarbon will be 34.8 downfield, and ortho, see upfield, it is shifting upfield, minus 12.9. Meta not much affected, para also upfield. This is due to the mesomeric effect. Again, I'll discuss in the factors affecting chemical shift values. See here also OCH3. OCH3 directly attached means anisole. For example, to benzene you add OCH3. Then what you will get? Anisole. So anisole, that OCH3 attached carbon, we call it ipsocarbon. For ipsocarbon, you can calculate it. Benzene value is 128.5, and to that you have to add this 31.4. I think I have calculated. I have given you the calculation. Yeah, I've given you the calculation. You see, 128.5 is the benzene chemical shift. To this, we are adding 31.4. See, 31.4. 31.4. So you get 159. So around 160. Simply remember any ipsocarbon which is attached to OCH3, it will be normally absorbed between 155 and 160. Simply, you can say if you are observing a signal around 160, you can say that a benzene ring is attached to oxygen if it is an unknown molecule. Okay, and C3, this is ortho. So ortho. Ortho shift minus 14.4. So that is 128.5 minus 14.4, it will be like this. And C4, not much effect, one I think, yeah, 1, and so 128.5 plus 1, 129.5. And C5 you see, C5 you values you see, minus 7.5. Meta, yeah, para, minus 7.7 it is given. Actually, we should add one minus 7.7. That's 1 minus 7.7 only it is added. So this is the value. So these are the values you expect for anisole. Not only for anisole, any alkoxy benzenes will be in the similar range only. And just representative example I have taken methoxy substitution, but any alkoxy substitution, OR, you can make it OR, roughly these values. Little bit variation will be there, plus or minus 2 ppm or so. So you can calculate for even disubstituted benzenes also. Like for example, I have given you here parachlorobenzonitrile. It is equivalent to the chlorobenzene and cyanobenzene. You can calculate this way. See, 128.5 is the base value. Suppose if you are calculating for this C1 carbon. So what you need to add, that the effect due to chlorine, increment due to chlorine. It is there here, yeah, in 6.2. 6.2 is calculated, yeah, 6.2. Okay, and then Cn to Cn, it is 4 position, right? To CN substitute, it is 4 position. So let us see CN 4 position, para 4.3. So you have to incorporate those values, 4.3. 128.5 is the base benzene value, and 6.2 due to chlorine, and 4.3 due to cyano. So you just add, you will get approximate value. Similarly, C2. C2 also you can calculate. C2 is 128.5 plus 0.4. 0.4 is a shift. I just I'll show you. Chloro 0.4. Ortho, see, 0.4 is there, and that we are adding. And then for cyano, it is meta. For cyano, it is meta. So let us see. Meta 0.6. So that is what we have added, right? 0.4 and 0.6, and this is the value. Okay. Similarly, delta C3, this one, C3 for chlorine it is meta, for cyano it is ortho. So let us see chlorine meta. How much? 1.3 you have to add. Cyano it is ortho, minus 16 actually. Yeah, that is anisotropic effect again here. See. Minus 16 we are adding 110.6. So why you must just now I told you, if it is attached to alkyne carbon, S-linic carbon also, that is triply bonded carbon, right? So upfield shift will be observed only in case of iodine, heavy atom effect, bromine, heavy atom effect, and cyano, anisotropic effect. Only in these 3 cases we observe upfield shift on the ipso carbon also. Okay. So that way you can calculate the chemical shifts of monosubstituted benzenes, disubstituted benzenes. But always remember these tables, you need not remember. Nobody will be asking you to remember these tables. If they are asking you to calculate the chemical shifts, they will give you the values, increment values. You simply have to substitute and get the values. That's all. Okay. So para substitution also you can get it, even for other substitution also it is possible, but let us not go in deep into details of it because that is not in your scope of the syllabus. Now, I am showing you the chemical shifts of compounds with carbonyl groups. Carbonyl groups. Okay. So different different compounds are there in organic compounds which contain C double bond O. Aldehydes, ketones, carbonic acid, acid halides, esters, anhydrides, amides, carbonates, so many are there, right? Oxygen. And these are the ranges. These are the ranges, just approximate ranges. You must remember most important are aldehydes, ketones, carbonic acids, amides, and nitriles. Most important. The rest all amides and nitriles are important. Acid halides also, they fall in the same range as esters. So these are important. Nitriles, oxygens, okay, they are important, but not that much. Okay, nitriles always you see upfield shift than benzene is observed. This is due to anisotropy. This just values I'm just showing you some representative values. See this the dioxane, you see it is attached to oxygen. I told you, when a carbon is attached to oxygen, it will be shifted downfield around 60 you can get. So here 66.5. See here it's an amide carbon, so 165.5. So just compare those values whether they are. Why I am giving you this is whenever you see a molecule, you should be able to assign the chemical shifts. Chemical shifts are given and the structure is given. You should be able to assign various chemical shifts to various carbons that are for that molecule. That is very important. So that is why these values are given. So sometimes methyl, ethyl, ether, only values will be given. You have to assign. So 57.6 cannot be this terminal one because the carbon which is attached to oxygen will be downfield. Here, this also you compare. I told you terminal and internal. Terminal always slightly upfield than internal one. See here 57.6, here it is 67.9, like that. Okay. This spectra also. Spectra also I am showing you how the normal C13 NMR spectrum looks like. This one ethanol. Ethanol, 2 carbons are there. One CH3, C around 20 C, and around 60 is oxygen attached to carbon. In ethanol, 2 non-equivalent carbons are there. So 2 signals, and one is around 20 and the other one is around 60. This is toluene. You see, in toluene, one CH3 is there. Aliphatic carbons is around 20, and aromatic carbons you see in fall in this range. And this is the ipso. That's what I was referring to. Ipso always downfield, which is attached to CH3. So these are aromatic signals. So whenever you see a spectrum, if you find signals in this region beyond 128 or so, 125, 128, you may think that an aromatic ring must be there in the molecule. Similar to proton NMR. In proton NMR also, beyond 7.7, if you get signals, we think that we confirm that aromatic nucleus is present in the unknown molecule when you are solving new problems. Okay, so just for that purpose, these ranges are very important. If you don't find any signals here, that means no aromatic ring is present in the molecule, and only aliphatic. See here, though no ring, no signals in the aromatic region. Only aliphatic region you find signals, because no aromatic ring in ethanol. Whereas in toluene you have aromatic ring, therefore you will get aromatic signals. This is alkyne, butane. Again, aliphatic, these are acetylenic. Acetylenic, one is terminal is upfield, then internal. In butane, 2 acetylenic carbons are there. One is that is C1 and C2. So C1 is upfield, C2 is slightly downfield. Their C usage are upfield than normal 128.5 or 123. 123 is ethylene, right? And if they are upfield than 123. So that means this is due to anisotropic effect. Okay. Just for reference, camphor. See, all are non-equivalent carbons only. C13 NMR of camphor is given for reference. So all are non-equivalent carbons only. Therefore, all carbons are appearing as singlets. Only these two, C9, which are very close, 43.29, 4, C3 and C4. 4 and 5. Right? They are very close, that's all. It's just for reference I am giving you. So that is how normal C13 NMR looks like. Broadband decoupled C13 NMR. Here no multiplicities are given. All non-equivalent carbons are giving you singlets. 220. This is for what? This is for carbonate. See, ketonic carbonate. Okay. You just see this for another reason also I gave you this example. Compare a proton and NMR. So much overlapping, you see. All are together. See the C13 NMR. It is quite resolved. Different, all signals are appearing. Whereas in proton and NMR, there is so much overlap, very difficult. Only ABC, only 3 CH3s you can assign. But other, these CH2, 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 CH proton, all these are coming as multiplied. Actually, you cannot make out anything from this. So it's quite complex. Whereas C13 NMR is quite simple to interpret. So that is the difference. Okay. No, I am showing you this chemical shifts of some deuterated solvents. These are same like proton NMR. Here also we use similar solvents depending on the solubility of the sample. So chloroform, deuterated methanol, deuterated DMSO, DMSO D6. Okay, all these. Benzene, when deuterated benzene also we can see, deuterated acetone also we can see, we can use, etc. So I'm just giving you some of the solvents, CD to Cl2. So that's this carbon signal 53.1. So multiplicity is 2Na plus 1, 2Na plus 1. Based on that rule, you can find the multiplicity. In spin-spin coupling, I'll tell you how you can calculate the multiplicity. But it is similar to proton NMR, 2NAi plus 1. 2 into N is a number of nuclei that are undergoing coupling. 2 into 2, 2 N is 2, 2 into 2, A. This 2 into 2 plus 1. 2Na plus 1 is 4 plus 1, that is quintet, 5. 5 multiplicity is 5. That's quintet. CdCl3, you see, T I value is 1, 2Ni plus 1, 2N, it will be 2 into 1 plus 1, that is 3, it's triplet. Okay, it's like that you can calculate. Similarly, CD3OD, 3 Ds are there, so it will be septet. And this is unresolved septet. DMSO-D6 also a septet. Sometimes they will ask what is the multiplicity of the signal in DMSO-D6 in C13 NMR. In such cases, these values will be important for you. You can remember them. You can, in fact, yourself you can calculate also. See, this is another thing you need to, and I should be able to assign the values. I told you, assignment of chemical shifts. Normally, structure is given, values are there. So you need to assign. One, suppose if you are observing the spectrum of furan, you will get two signals, 109 and 192. So you may think which one is 192, which one is 109. It is definitely 192. It should be definitely. It's aromatic carbon and also attached to oxygen. Therefore, it will be this one, 192, and the other one is upfield signal. This is due to again mesomeric effect, electron delocalization effect. We will discuss that again once again. So like this, the carbonyl shift C219, you see, you should be able to assign, and 39.7, 37.9 and 22.7. So 37.9 will be attached to carbonyl group, and this is meta, slightly far away from carbonyl. So electronegativity effect of this will not be that much on this carbon. So when a structure is given and the data also is given, you should be able to assign the structures also. And you should be able to assign the chemical shifts to various carbons that are present in the molecule. And if you record the spectrum also, the same thing you should be able to assign. Next. Yeah, that's all about calculation of chemical shifts. You can calculate the chemical shifts of alkanes, alkenes, and alkynes also, and aromatic compounds also. But very important are alkenes and alkenes, examination point of view. And others also, they are important, but even if they ask you to calculate, they will give you the values. So just remember ethylene value, methane value, and benzene value. So to that you have to add incremental shifts. That's all. So what are the factors that affect the chemical shifts of carbons? Just similar to your proton NMR. You can different factors affect the chemical shifts of various carbons in C13 NMR. So similar to that, electronegativity effects there, hybridization, anisotropy, heavy atom effect, hydrogen bonding, isotopic effect, and solvent shifts, electron deficiency, effect of pH. All these factors affect the chemical shift. We will discuss them one by one. Okay. So hybridization, how does it affect? You have three types of hybridizations in carbon. So sp3, sp2, and sp. So sp3 hybridized carbons generally fall in this range in the spectrum. sp2 carbons between 116 and 140, like ethylene, benzene, all these carbons will be observed in this range. sp carbons will be observed 65 to 110, and this is due to the anisotropic effect of triple bond. See, examples I have given you. Ethane is 5.7. 5.7 ppm. Again, 2 times this delta value is shown. Print a mistake. It's 5.7. Okay. And ethylene, you see 123.3. This value you need to remember. And this also you need to remember 128.5. Now, alkynes roughly this way around 67, 7, and this is 84. See, this is terminal alkane and internal alkane. Always terminal alkane is upfield and internal alkane. Okay, so these are the hybridization values, from the chemicals. Suppose if you don't know the hybridization, if it is an unknown molecule and you observe the signal at around 128.5 or 130, so what is that you can guess? there must be aromatic ring in the compound. And similarly, if you are not getting any signal in this ring, 123.3 or 128.120 to be precise, if you don't get any signal, only aliphatic signals are present. That means there are no aromatic rings in the molecule, and only it is an aliphatic compound. Like that, you can interpret like that way. Now, influence of electronegative groups or atoms on CS. How electronegative groups or atoms influence the chemical shift. And chemical shift, similar as in the case of proton NMR, here also generally chemical shift is affected by the electron density, because electron density around the nucleus, that electrons circulate, and they result in shielding of the nucleus from the external magnetic field. That is why it is shifted normally upfield. So the C13 nucleus also is shielded by the circulating electrons around it. This is known as local diamagnetic shielding. It is just similar to proton NMR. Only thing is what we are here, we are observing the C13 nucleus. That's all. So the chemical shift increases as the electronegativity of the attached atom or group increases. Simplest example we take methane. Methane, I told you, minus 2.5. So it is attached to chlorine. Then its chemical shift will be more than methane. Definitely, because chlorine is electronegative group, and it will shift the electron density from the carbon away from the nucleus. Therefore, less diamagnetic shielding. Therefore, it will be shifted downfield. So chlorine, suppose methanol, methyl chloride and methanol. Methanol OH is there. In methyl chloride, chlorine is there. So which one do you think will be more downfield? Methanol will be more downfield, because OH is more electronegative than chlorine. Similarly, you compare with methyl fluoride. Which one will be more downfield among these three? Definitely methyl fluoride, because fluorine is more electronegative. So that is what I am showing you. So the more the electronegativity, more is the downfield shift. That is general rule. The electronegative substituent decreases the electron density. Why it is so? Because the electronegative substituent decreases the electron density around the carbon, and therefore produces downfield shift. So that is the reason why, since the electron density is decreasing by the attachment of electronegative substituent, then that de-shielding, diamagnetic shielding effect is less. Therefore, it is de-shielded and shifts. The chemical shift is shifted to longer, higher frequency. Okay. Here one more point you have to be noted is the effect of electronegative substituent is more on carbon chemical shift than on hydrogen chemical shift. Proton NMR also the same thing happens, but it is less there, it is more here. Why? Because carbon is directly attached to electronegative atom or group, whereas proton, it is not directly attached. In case of proton, it is indirectly attached via carbon. So 2 bonds away. Here it is directly attached, only 1 bond away. That is the reason why the effect of electronegative substituent is more on carbon chemical shifts than on proton chemical shifts. And if that's what this also I told you, electronegative group causes normal downfield shift for alpha and beta positions, and upfield shift for gamma carbon due to gamma Gaussian interaction. See some representative examples here I am showing you. See ethanol 5.7, and methyl ether, here oxygen is attached. See so much shift. Roughly 54-55 ppm downfield shift. See here also ethylamine, ethyl chloride, ethanol, and ethyl fluoride. You just compare the values. Downfield shift increases as the electronegativity of the atom increases. Atom or group increases. Here you see here 35.9. Chlorine is more electronegative, therefore 39.9 shift. And hydroxy group, oxygen is even more electronegative than chlorine, therefore 57.9. And same carbon, ethane carbon only, but these electronegative substituents shift the chemical shift, and in that also electronegativity of the group or atom influences the chemical shift. See, fluorine is maximum because fluorine electronegativity is maximum than other elements. Okay. So always remember, parent compound, parent alkane, and electronegative group or atom attached. So definitely there will be downfield shift due to the decrease in diamagnetic shielding. Okay. Anisotropy. The name itself suggests there is something anisotropic, not isotropic, which is not anisotropy means unequal. Isotropy means equal. What is equal or what is unequal here? Here chemical shifts of some types of carbons like alkene, acetylenic, aromatic, nitrile, and carbonyl carbons, cannot be explained by electronegativity concept alone, because benzene 128.5. So electronegativity will not contribute to that much downfield shift. Similarly, ethylene 123.3. Even there also electronegativity concept alone cannot explain that 123.3 shift. Therefore, there comes another term called anisotropy. Here, this is due to the circulation of pi electrons that are present in these molecules. See, all these groups, alkenes, aromatic compounds, acetylene, nitrile, carbonyl, all these contain pi electrons. So, in presence of applied magnetic field, they circulate. Yeah. Like this, I am showing you different groups. This is the benzene. So pi electrons are there. In the presence of applied magnetic field, these electrons circulate like this, and they generate secondary magnetic field like this. The magnetic lines of force originate like this and go like this and end up there. So like this, these are called magnetic lines of force, we call it. Similar to proton NMR, there also see same thing you have observed. See, induced magnetic field, we call it. Induced, that induced field is coming from where? From the circulating pi electrons. When the electrons are circulating, that will generate a magnetic field, that induced magnetic field. It will be in the opposite direction when they are originated. See, opposite direction of the applied magnetic field. And as they go up, they will be here in this region, they will be in the same direction. And when again they are ending, there also they are opposite direction. So that means, that the carbons here in this region experience more magnetic field at certain positions and less magnetic field because they are opposing at certain areas around the molecule. So from below and above, they experience slightly less applied magnetic field, and at the periphery here and here are these carbons. At the periphery, they experience more magnetic field. More magnetic field means more crystal frequency. More crystal frequency means it will be observing at a higher radio frequency. Downfield shift. We call it downfield shift. So what is anisotropic here? The secondary magnetic field that is generated by circulating pi electrons is not isotropic. It is not same everywhere around the molecule. It is different at different places. Above and below, it is opposing the applied magnetic field, and at the periphery, it is reinforcing the applied magnetic field. Therefore, at the periphery, the nuclei experience more magnetic field, and above and below, they experience less magnetic field, resulting in upfield shift here and downfield shift at the periphery. That is the reason why aromatic carbons are shifted downfield 128.5. Benzene 128.5. Actually, these diagrams are shown for whether it is proton or carbon, the same diagrams. Okay. Only thing is, we will be taking protons in proton NMR. Here we are taking carbons. That is the only difference. See, benzene. So this plus means upfield shift. Minus means downfield shift. Here also you see alkene plus upfield shift, and minus is downfield shift. And here carbonyl group, just above and below. As aldehyde, you see, is downfield. When you compare aldehyde carbon, it is a downfield as compared to benzene. Will be anisotropic. Here in acetylic, the circulating pi electrons act in a different way. They circulate like this here. They are not circulating like this. They are circulating like this. So they upfield at the carbon or hydrogen, acyclic hydrogen. So these are the diagrams of anisotropy. What is anisotropic here? The secondary magnetic field, generated by circulating pi electrons in all these molecules is not same around the molecule. It is more at some places and less at some places. So that results in downfield or upfield shifts in the molecule. Okay. And next is, see, and the anisotropy examples I am showing you. Benzene already told you 120.
విజయలక్ష్మి మేడం మీరు మైక్రోఫోన్ మ్యూట్ చేయండి. విజయలక్ష్మి అంటే మైక్రోఫోన్ ఆన్ చేసింది మేడం, ఆమె దగ్గర నుంచి వినపడుతుంది వాయిస్.
నాకు డౌట్ వచ్చింది. ఓకే. So, anisotropy examples I am showing you here. See, benzene 128.5, ethylene 123. These values you remember. And aldehyde 190, around 190 only. Benzaldehyde or even substitute benzaldehyde, they will be in this same. Benzonitrile, it is 190 due to the anisotropic effect of C. And see, it is due to anisotropic effect. 120, actually it is upfield than 128.5. Why so? Because acetylenic pi electrons is not acetylenic, nitrile pi electrons circulate like this and generate applied generates that is opposing the applied magnetic field of the carbon. So I'll just remember as a thumb rule, any carbon that is attached to triply bonded carbon, it will be shifted. Here you see ring current. I told you benzene ring above and below. If any carbon or protons are there, they are shielded. So here you see, due to this ring current, you can just see here above and below, plus upfield shift. And that is what is shown here. Above, it is the CH2 is falling in this planar benzene structure above. So it is shielded. And this CH2, they are normal, they are not in the shielding zone. We call it shielding zone. Above and below the benzene ring, we call it shielding zone. Okay. Similarly, you see, these are 10 pi electrons, ring current here. Also generates ring current, and that also generates secondary magnetic field, and that magnetic field opposes the applied magnetic field above and below. So it is also aromatic, isn't it? So above CH2, this is shielded. Even if it is below also, if there is any carbons above or below, they will be shielded. That is due to anisotropy. So always remember what are the groups that contribute to the anisotropic effect. Benzene, and generally double pi electron containing groups like alkenes, benzene, acetylene, C triple bond N, and C double bond O. These are the groups that contribute to the anisotropic effect. And benzene, it is more, and aromatic. Benzene means benzene is a representative aromatic compound. So aromatic compound is quite high. That ring current is quite high. That is why aromatic carbons experience downfield shift, and the carbons which happen to be above or below the benzene ring, as in this case, paracyclophanes, like this. If it is falling above, just above the ring current, aromatic ring, therefore it is shielded. This also is just above the ring current, it is also shielded. So this is the anisotropic effect, similar to your proton NMR. Next is mesomeric effects. Electron delocalization effects. When an aromatic ring or any doubly bonded system or triply bonded system is attached to electron releasing or electron withdrawing groups, what happens? That will change the electron density around the carbons. For example, electron donating groups attached to benzene ring shield the ortho and para carbons. Why? Because electron donating groups in the benzene ring, they increase the electron density at ortho and para positions. So increased electron density means what? Increased shielding. Therefore, they will be shifted upfield. And electron withdrawing groups cause de-shielding effects. Why? Because they withdraw the electrons away from the carbon. So carbon electron density and the nucleus of carbon nucleus experiences less electron density around it. Therefore, shielding will be less. So de-shielding. And electron delocalization in unsaturated systems may result in increase in electron density. This is what the generalized statement, or decrease in electron density at some carbons, depending on the substitutions. Okay. Whether it is electron donating or electron withdrawing. So that will affect the chemical shifts of the carbons. Okay. Since the chemical shift is dependent on the electron density. Why so? Because the chemical shift is dependent on the electron density around the carbon nucleus. These delocalizations result in off-field or down-field shifts. I am showing you with some examples here. Electron delocalization. First, we'll take vinyl ethers. Okay. Not only benzene, any molecule where doubly bonded, triply bonded carbons are there, they will also will participate in. I mean, the substituents attached to these groups also will result in the electron delocalization. Will undergo electron delocalization, resulting in increased or decreased electron density around particular carbons. For example, vinyl ethers. You say vinyl ether double bond is attached to alkoxy substituent. Here I'm just showing you methoxy, this one, methyl vinyl ether, methyl propanyl, propanyl ether, methyl propanyl ether. If CH3 is not there, it is methyl vinyl ether. So yeah, it is there here. So here, this electron delocalization, the in electrons of oxygen are moving here, and these double bonded electrons will move there. So this carbon gets what? Negative charge in one of the resonance structures. Okay, so that means electron density is increased here. Similarly, here also this carbon gets more electron density as compared to this. So see, compare the values. This is 84, this is 153. Here two factors are contributing. One is electronegative substituent, the other one is electron delocalization. Okay. It's electron. Electronegative substituent is contributing. Electron delocalization effect is contributing upfield shift to this carbon. Okay. Similarly, same effect is observed in alkynyl ethers also. Only here triple bond, here double bond, here triple bond. Same thing. See, so much difference. You see, 28 and 88. This electron delocalization results in increased electron density. There, here also increased electron density, 23. So much difference, you see. So that effect is observed. This is due to the increased electron density around a particular set of carbon due to the delocalization of n electrons. Here you see, this is just, you can generalize it. If it is not need not be methoxy, it can be any alkoxy. Okay. Now, another type of compounds, alpha beta unsaturated carbonyl compounds, where delocalization can take place. But here in the opposite direction. In case, it is increasing the electron density at the beta carbon, whereas here it is decreasing the electron density at the beta carbon, alpha and beta. So beta carbon electron density is decreased. See. So this is de-shielded. So this carbon is de-shielded. Suppose if this carbonyl is not there, this is same as normal alkene carbon only. So it will not be de-shielded. It will be coming around 123, like that. But here it is de-shielded. That is the reason why it is coming at 136. You see, it is here 129, more than ethylene. That is due to electron withdrawing effect of the carbonyl group. Here also you see cyclohexenone, carbonyl carbon 198, and among these two alkene carbons, see, alpha and beta carbon, 150. Beta carbon is coming at 150. Why? Because due to the delocalization, carbonyl electrons will go there, and these electrons will go there, and this will experience a de-shielding, and this will have electron density less than the other carbon. Therefore, it will be shifted downfield or de-shielded. In the rest, all not much affected. Similar to previous. But here you also see cyclopentenone. Here also beta carbon is shifted downfield as compared to alpha carbon. If this carbonyl is not there, let us just assume that it is cyclopentene. This the chemical shift values will not be like this. It will be like ethylene value. Okay. Same here. Ester carbonyl, that is also due to delocalization. This will beta carbon is deshielded, and here also beta carbon is deshielded due to the delocalization of CW bond, like that. So even acetophenone, in acetophenone, ortho and para carbons are deshielded, like that. So I'm showing you the aromatic compounds also. See, we have seen aliphatic vinyl ethers. Here I'm showing you aromatic compounds where phenols and alkoxy benzenes also similar. You know, these electrons moving like this, mesomeric effect. So at ortho and para positions, electron density is increasing. So that is the reason why see ortho and para carbons you observe 116 ppm and 120 ppm lesser than 128.5. Lesser. If OH is not there, it would have been around 128.5, right? Benzene. And because of OH, due to delocalization effect, it is coming at 116 and 120. This actually unknown carbons, unknown molecules. If you see in the C13 NMR, you can in fact predict whether they can undergo electrophilic substitution or not very easily or not. Well, because if unknown compound is there, if you observe aromatic ring, some signals upfield shift, then you can say that electron density is more their particular carbons. So definitely, and there is a possibility of increased electrophilic substitution. I mean, tendency to undergo electrophilic substitution in such cases. Okay, so that will come in application part anyway. You just observe aromatic ring when it is attached to OH or alkoxy group. The same thing happens. The electron density at ortho and para carbons is increased, and therefore upfield shift is observed. See the ipsocarbon, you see 155 because of the electronegativity of the OH, and metacarbon is not much effect. Next. Substitute. See, these are the substituted aromatic compounds. Just to explain you further about the effect of these delocalizations and mesomeric effect. See, amino group also n electrons are there. They are given into the ring. Ortho and para positions experience. If you write the resonance structures, you will see ortho and para positions more electron density than the meta. So that is what is observed here. Ortho and para are of field 116 and 119. And here you see alkoxy. I told you just now, ortho and para of field 114.1 and 120.8. Okay, and ipsocarbon you see 159.9. Here also ipsocarbon is 147.7, lesser than was because electronegativity of nitrogen is less than oxygen. This is less than this ipsocarbon is observed at 140.7, 147.7, lesser than 159.9, which is methoxybenzene. Okay, so like that you should be able to compare. And now these are benzene ring is attached to electronegative groups. I mean electron withdrawing groups. These are electron donating groups. These are electron withdrawing groups. So they will take away the electron density from the aromatic ring. So they will decrease the electron density at ortho and para positions. And with the result at ortho and para carbons, see, ortho and para carbons are shifted downfield 130 and 132. Okay. NO2, you see, maximum. NO2 also takes away the electrons from the benzene. That is it is deactivating, and you can observe that here at ortho and para position electron density is less. Therefore, the chemical shifts are observed more than benzene, more than 128.5. It's 133.8 and 134.5. So that is the reason why any group, if it is electron withdrawing, it will decrease the electron density at ortho and para positions of the benzene ring. If it is electron donating, it will increase the electron density at ortho and para positions of the benzene ring. So if electron density is increased, upfield shift. If electron density is decreased, downfield shift is observed. Next, this is not much, very little difference will be there, but conjugation of double bond also results in the off-field shift of nearest alkene carbons because of the electron density will be more here in conjugated electrons, the conjugated alkenes. Therefore, slightly off-field shift will be observed. Heavy atom effect, heavy atom effects mean bulky atoms attached to carbon that will give off-field shift. Bromine, you see one bromine 10 ppm, 2 bromines 21.4, 3 bromines. See the trend. Dibromo 21.4. Tribromo, it should be even more because 3 bromine atoms more. If it is only dependent on electronegativity, CHBr3 should be more than this. But because of heavy atom effect, because bromine is very big, and that will increase the electron density around the carbon. That is why upfield shift. See, 4 bromines, it is even upfield, the minus values, it has gone to minus values. You just compare with chlorine. In chlorine, this heavy atom effect will not be observed. And as the number of chlorines increases, downfield shift is observed. Tetrachloromethane will have maximum chemical shift as compared to other trichloro, dichloro, and monochloromethane. Okay, that way. Only bromine, iodine will show this effect. When iodine is attached first itself, you see this iodine is even bigger than bromine, therefore minus 20.7. Methyl iodide, actually methane is minus 2.5. Methyl iodide, when iodine also is electronegative only, but that electronegativity effect is cancelling the heavy atom effect. Therefore, it is upfield. Similarly, 2 iodines, more negative values, 3 iodines, even more negative values, CI4C, how much negative value it is, minus 292.5. Only these 2 atoms will have such effect, and all other will not have no other atoms have that much effect. Only electronegativity plays major role there. Here, more than sometimes more than electronegativity, heavy atom effect is more here. Next, hydrogen bonding also influences the chemical shift because hydrogen bonding also affects the electron density. See, this is no hydrogen bonding, 191.5 aldehyde carbonate. Here, hydrogen bonding is present, intramolecular hydrogen bonding. Therefore, it is shifted about 5 ppm, 5 to 6 ppm downfield or higher frequency, 196.9, you see. And here also, you see 195.7. 204 points, so roughly around 5-6 ppm. So from this also you can understand whether intramolecular hydrogen bonding is present in the molecule or not. When there is, and another thing also, you can, in fact, that I will discuss in the application part. You can also check whether you have intramolecular hydrogen bonding or intermolecular hydrogen bonding, depending on the chemical shift values. Okay. Isotopic effect, isotopes, just this is also very small, not much, but it will be observed, and it is useful in especially very special cases where other data is not able to give you enough information, and then this deuterium labeled ones, when you are trying to identify deuterium labeled compounds, this minute differences also will be very helpful, but not normally for structural elucidation. Okay. So in very special cases, definitely they will also come into rescue. But the effect is very small. See, 53.8 and 52.1. 2 hydrogens are replaced by 2 deuterium atoms. So heavy, that isotopic effect will shift upfield. 78, 77, just 1 ppm. CD3 body 14 and here 0.9. That's all. Okay. So heavy isotopic shift, heavy isotopes will shift upfield, will have upfield shifts. This is not isotopic effect, this is heavy atom effect. This now we discussed. Electron deficiency. Electron deficiency also contributes to, as I told you, chemical shift is always dependent on what? It is dependent on the electron density around the nucleus. Electron, when there is electron deficiency, that means the upfield shift or shielding is less. is it not? So when in carbonium ions, there is no electron deficient. Carbonium ions are electron deficient. Therefore, definitely there will be downfield shift. You see, carbonium ion 320. So in special cases, I told you carbon-13 chemical shifts. You can they can go beyond 240 up to 350. I said no. So in carbonium ions, it will happen. Electron deficiency also influences the chemical shift, and in fact, electron enriched. Density is more like in carbonium ions. That will also affect the chemical shift. So that in the application part, we'll be discussing with examples. So that's all. These are the factors that affect the chemical shift. Since time is nearing, so what are the factors that affect the chemical shift of carbons? Hybridization. So sp3, sp2, and sp, they will have different chemical shift values. And sp3 upfield towards right side of the nearer to TMS, and sp2 in between. sp in between, and sp2 towards farther end of the TMS. Okay, and electronegativity affects the chemical shift. The more the electronegativity, more is the downfield shift. And next, anisotropy. And there are certain groups that will result in anisotropic effects of the secondary magnetic field by circulating pi electrons, like alkenes, aromatic compounds, alkynes, and carbonyl compounds, acetylene, nitriles, etc. These electrons, pi electrons present in these groups, will undergo circulation in presence of applied magnetic field. So they will have, they will generate secondary magnetic field. That magnetic field is different at different places around that in the molecule, in the space. So if the carbons or any group in the structure, if it falls in the shielding zone, upfield shift will be observed. If it falls in the de-shielding zone, downfield shift will be observed. Therefore, benzene carbons are in the de-shielding zone, therefore they are observed downfield, and 128.5 is the basic benzene value, and other aromatic compounds also fall in this region only. And alkynes, upfield shift is observed because that carbon falls in the shielding zone of the pi electrons, circulating pi electrons of acetylene group. Similarly, C triple bond N also same thing. The carbon that is attached to C triple bond N will be observed upfield. Okay. And these are very important. And another important one is delocalization effects. Any group, due to delocalization, if it is increasing the electron density around particular carbon, then upfield shift is observed. If it is decreasing the electron density of particular carbon, then downfield shift is observed. In vinyl ethers, beta carbon is upfield, whereas in alpha beta unsaturated carbonyl compounds, beta carbon is downfield because decreased electron density. So always these things, delocalization effects matter. And even the groups are attached to benzene ring. If the group that is attached to benzene ring is increasing the electron density at ortho and para carbons like OH, OCH3, and H2, that will shift the carbons chemical shift to upfield. And if it is electron withdrawing groups, carbonyl group or ester group is attached to benzene ring, it will decrease the electron density at ortho and para carbons. Therefore, downfield shift is observed. So these are very important, especially in structural elucidation. And now it's almost time is up, and just introduce couplings. C13 NMR spectroscopy. This carbon-13 NMR also undergoes coupling, and coupling is mainly two types. Heteronuclear couplings means the coupling between carbon and other nuclei other than carbon, that is hydrogen, fluorine, phosphorus, etc. And homonuclear couplings. Homonuclear coupling means a coupling between same type of nuclei, carbon-13 and carbon-13. So we will discuss this in the next class. Okay. And okay, that's all for today. I'm just closing it. Thank you.
Thank you, madam.
Okay, welcome. If any doubts, you can actually
మేడం నోట్స్ పెట్టారా అది గ్రూప్ లో పీడిఎఫ్
ఏంటమ్మా
పీడిఎఫ్ పెడతారా మేడం నోట్స్
ఇది సేమ్ మీ మెటీరియల్ అంతా ఉందమ్మా ఇదంతా నేను ఎంత చెప్పిందో మొత్తం మీ మెటీరియల్ ఉంటుంది కదా ఇట్ ఈస్ దేర్ యాక్చువల్లీ ఐ ఓన్లీ హ్యావ్ రిటర్న్ దిస్ మెటీరియల్ ఓన్లీ సమ్ ప్రింట్ మిస్టేక్స్ విల్ బి దేర్ ఇఫ్ యూ వాంట్ యు నో ఐ విల్ గివ్ యూ మై నంబర్ మేబీ మెయిల్ యూ కెన్ ఎనీ డౌట్స్ యూ కెన్ డిస్కస్ నోట్స్ అంటే సేమ్ మీ స్టడీ మెటీరియల్ ఉంటుంది కదా అదే నథింగ్ just some examples maybe I'll be taking note, and if you want further information maybe we can discuss later. My number or my ID you can take from Koteshwara sir. Koteshwara sir, you will be in touch.
yes ma'am.
You can ask him and I can clarify your doubts. Notes means the same thing because the same material.
Okay ma'am.
Yeah, because in PowerPoint I cannot give you because here complete will not be there, no. Only bullets type will be there. So material in the material only more information will be there, and some problems. If you want extra problems, we can in fact the textbook I have given you. Actually, this especially this E13 NMR I only have written. So everything is there in that book. Okay.
Okay, madam. Thank you.
You are in like Ambedkar Open Institute student only?
Yes, ma'am.
For any confirmation or notes, you ask Koteshwara sir. He will guide you and he can give you actually PDF form if he is having. He can give you PDF. I think he must be having, but that PDF is also same thing. Same what is there in your books. You must be having your books, no?
Yes, ma'am.
Okay, that's all for today. Next, in the next class, we will be discussing couplings in C13 NMR and applications of C13 NMR. So that finishes. Most probably, we'll be able to finish C13 NMR in the next session. Okay. Bye. That's all for today. Bye.
Okay, ma'am.
Any doubts? You can discuss here if you want.
Okay, ma'am.
Or you can put in the chat box, or you can write down on the paper, and if any doubts are there, first go through the material and then you can ask me.
Okay. Okay, madam, we can close this session.
Okay, I'm just leaving. Bye.
Yes, ma'am.